So just to give you an overview or some fundamental idea. Yeah, if you have questions, well, feel free to interrupt anytime. So you don't have to wait until the end. I want to make sure that you can follow the talk very well. Somehow this Zoom, this okay, how to minimize this. Okay, put it to the bottom. Droplet microfluidics. So basically, my work were about droplet-based microfluidics. We know that we don't have to have droplets inside a microfluidic device. For example, in the gradient generator or mixer, it's all about 2 or more miscible fluids. But when we talk about droplet microfluidics, we mean like we have at least 2 immiscible fluids, oil and water, or we can have multiple phases. Somehow, couldn't control. Yeah. So these are what we have learned. There are, in general, 2 types of microfluidics devices that are most widely used in the society. One is the PDMS-based, which you make them by soft lithography. And the most advantage of a PDMS-based device is their capability to generate monodisperse droplets at very high frequency. I mean, also monodisperse single phase droplets, meaning just oil in water or oil in water or water in oil drops, just a single emulsion. We call them single emulsion. Also, another advantage is that you can integrate different kinds of components onto the PDMS devices. For example, as you see from this picture on the top left, we have those. So there are 4 identical devices on 4 identical channels on this one device, and you see those black parts. Those are electrodes. So and the right picture on top is the image that you can see under a microscope. So again, the 2 black part are the electrodes. So basically, this device can, well, shine laser onto each droplet. The laser is very high frequency, so make sure that every droplet can be exposed to the laser. So if the droplet contains a certain type of protein, it will be triggered by the laser, and therefore they go to one type. So from here, I couldn't control my cursor. Yeah, I hope you can see my cursor here. I play. Oh, somehow, wow. I don't know why all the videos can play. So there's a Y junction here. So if the droplet has the specific protein, it will go to this branch, the top branch. Otherwise, it goes to the other branch. So this is very useful for biological applications. We call it high throughput screening. And another type is glass capillary based. This is a real picture of a typical double emulsion. Yeah.
What's it called, you said?
What is what?
The PDMS image that's not playing. What's the process called?
What's the process called? High throughput screening.
Okay.
So basically, you can screen a few hundred droplets per second. So you can have, for example, 300 to 500 is typical, definitely doable. You can have 300 droplets passing this electrode every second and then source them. So as I said, if they have that specific protein, they go to one channel. If not, they go to others, you separate them. A few hundred droplets per second, very high speed, very high frequency. And okay, so in the bottom is the glass capillary based microfluidics. Later on, I could introduce a little bit more. So you basically you buy commercially available glass capillaries, then you use a machine, so-called capillary puller, to pull the device, to pull the capillary to have a tapered shape like this. And then you may need to use the sandpaper to sand the tip a little bit to make them flat, or to the desired radius size that you want. Then you assemble them within a slightly larger square cross-sectional capillary. And the inner dimension of that square capillary is just slightly larger than the outer radius of this circular capillary. So it's relatively easy to have the coaxial assemble. But you still have to do it under a microscope, and to make sure that, for example, the distance between these two tapered capillaries are in the proper distance. Also, you make sure the size, everything is okay and is in perfect coaxial assemble. Then you add this yellow needles as the inlet or outlet. Sometimes this is the outlet as well. So this capillary, one of the capillaries will be outlet, and these will be inlets. For double emulsions, we need the 3 phases. So the inner phase, so next slide, you could have, this is a nice picture of a double emulsion droplets, meaning each droplet has 2 layers. And in this case, we added some fluorescent dye in the inner phase. You see an inner droplet surrounded by a larger droplet, which as a whole suspended in the continuous phase. In this case, we have an water in oil in water double emulsion system. It has the innermost water-based core surrounded by an oil shell. Then this double layered droplets suspended in a continuous water-based solution. You may have, okay, so this is double emulsion, single emulsion, just 1 droplet, single droplets. You may have triple emulsion. Each droplet has 3 layers, or quadruple emulsion, 4 layers, or even quintuple, 5-layered droplets. Although, I mean, the application of this 4-layer or 5-layer droplets are still, you know, in question mark, but still, I mean, it shows that we can really control the structure of these droplets, and all of them are highly monodisperse. So you may include different active materials in different layers. For example, because this double emulsion droplets were proposed for targeted delivery application. Later on, I will show you a specific example. So you may include or encapsulate a certain drug or whatever active materials in the core, or if it's oil-based drug, you can encapsulate in the oil shell. Then at a certain condition, you can release them in a controlled manner. So these are multiple emulsion. Now, the application of drop-based microfluidics range from biology to material fabrication, also to study fundamental mechanical engineering or physics problems. Well, yeah, so for material, we can make nanometer-sized particles. We can make double emulsion and then transform them to solid shell capsules. So what we make is double emulsion. Every 2 layers are both liquid-based, but we can somehow remove the oil from the middle phase, so we can get a solid shell capsule. And also, people have been using microfluidics to make microcapsules with a solid shell to study the buckling effect. And another example is a microfluidic model porous media, which we have discussed in previous lectures. So today's lecture has 4 parts. Maybe I will skip one of them, maybe, or just quickly go through some of them if I don't have time to go to the detail. The first one is all about microfluidics enabled functional materials. The first one is about polyhedral microgel particles. Okay, there are actually more than 4 examples. So I list some examples from single emulsion, double emulsion, and then thin shell double emulsion, and then another example from triple emulsion. I will see how much time I will have. So the first one is about the fabrication of polyhedral shaped microgel particles. So people have been working on fabricating non-spherical shaped microparticles for a lot of different applications. For example, we may use them to study self-assembly problem, to study the rheology of particulate systems. We know that when we have particles suspended in a liquid, it changes the rheological properties of the liquid, viscosity, or maybe from Newtonian fluid to non-Newtonian fluid. And to study, and also the particle shape and size, shape, roughness, all matters. So the non-spherical macroparticles can be used to study these rheology of particulate systems. Or transport of particles through narrow channels. In particular, we may, also through narrow channels in porous media. These are all very relevant. The particles can be rigid, can be soft, if it's rigid, can have different shapes. And also the property structure relationship in materials. This is associated with the first self-assembly problem. When we have for example, sphere bed, we will have a large group of particles. And this large group of particles assemble together or maybe loosely packed together. And this larger macroscopic material composed of these small particles have a certain properties. And the property of this macroscopic material depends on the structure of the small particles. So non-spherical particles can be used to study this problem as well. And also it can be used as a delivery carriers of drugs or building blocks for engineered tissue scaffold if they are hydrogel-based materials. So traditionally, people have been using lithography-based approach to make non-spherical gel particle, I would say. I would focus on gel particle because it has a lot of different applications in drug delivery, in bioengineering. So what does lithography-based approach mean? So basically, we have a microfluidic channel with a very thin parallel plate channel, so a little bit wide, and the thickness of the channel would be the same as the height of the target particles that you want to make. So to make a hydrogel, basically we have the pre-polymerization solutions. You dissolve the so-called monomers, like the molecules before polymerization. They can dissolve in water, for example. You dissolve them in water at a certain concentration, let's say 5% or 10%. Then many of these monomers can be cross-linked by UV irradiation. So if you shine UV light onto it, of course, you need to add the cross-linker that I mentioned before, cross-linker and maybe the photoinitiator. So basically, when you shine UV light onto this solution, the photoinitiator can generate some radicals. That the radicals will help with the cross-linking or polymerization process. So okay, so you shine UV onto the solution, then the part that is exposed to the UV light will be cross-linked to polymer, to hydrogel particles. So then, okay, so we have this parallel microfluidic channel in which you have, you inject the pre-polymerization solution through this channel. Then you shine UV light onto this channel through a mask. The mask has the shape of the particles. For example, you may have a like rectangular mask with, let's say, multiple triangle shape. Then when you shine UV through this mask, only that triangular area, would be exposed to UV, right? So the solutions in that area will be solidified to become hydrogel particles. So after you shine UV for, I don't know, a few seconds, then you will have multiple particles formed in this channel. Then you continue to flow it. These particles will be flow out of the channel, and then you can collect them in a container. So through this way, you can make non-spherical hydrogel particles of any shape, but they are all 2D extruded because you just shine it through the mask. So for example, this is a triangle disc. This is a square disc. This is a hexagon disc. This is a little square. This is also a little bit high triangular prism, and this is also a high circular prism. These are all 2D extruded structures, right? Although if you use double layered microchannels, it's possible to make, you know, a 3D structured particles. It's usually relatively difficult to use this method to make truly 3D structured microparticle. So we are inspired by the dispersion systems of two immiscible fluid. So here, I mean, dispersion system of two miscible fluids means foams or emulsions. For example, this is a foam structure, very dry foam with a little bit continuous phase and a lot of bubbles. This is the corresponding emulsion system, basically droplets in a continuous phase. So when you remove the continuous phase to a large extent, these bubbles or droplets in the foam or emulsion system will have to deform, right? They cannot remain their spherical shape anymore. They have to deform, right? Then, so if we can, for example, for this deformed droplets, if we can cross-link them at their deformed state, then they can become non-spherical shaped particles, right? So this is what we are, what the strategy, our strategy is. So in nature, we usually see polydispersed foam or emulsions, meaning those droplets or bubbles are not the same size, and therefore when they deform, they also have all different kinds of shapes. However, if we have a monodispersed system, we have uniform sized bubbles or droplets, then we would, after they deform, they would have a beautiful structured lattice patterns like this, like in the honeycomb. Like each of this cell is a hexagon shaped. So inspired by this, because we can make uniform sized droplets from microfluidics. So our strategy is to first make the droplets that are uniform and then compress them, deform, make them deform. Then we polymerize them to form non-spherical shaped particles. Okay, so we start from the most simple structure, single layer droplets packing. We just collected the droplets, monodispersed size, within a parallel plate channel. So when there is a relatively, when the continuous phase is still there, so each of these droplets remains a circular shape, then we polymerize them, we can get the circular disc. If we further remove the continuous phase, so these droplets become hexagon shape, then we polymerize them, they become hexagon disc. We can also control the thickness of between the two plates to make the disc thicker and thicker, higher and higher, until we control the aspect ratio of the resultant hexagon disc or prism. Then we make it a little bit more complicated. We further increase the distance between the two parallel plates, so we can pack 2 layers droplets in between. Then when you have relatively more continuous phase, each of these droplets are still spherical. So this is what you will see under the microscope. You have 2 layered droplets. Each layer is in a hexagonal packing. Hexagonal packing means this one. This is the densest packing that you can get for monodispersed spheres. So you have 2 layers of this hexagonal packing. And also to reach the highest density, packing density, each droplet will sit in the middle of 3 droplets from the other layer, right? So that's why you see this structure. For example, this droplet sits in the middle of these 3 droplets. Okay, so then next step is to remove the continuous phase. Then the spherical droplets have to deform. Then you will see this structure. Each of them deform to hexagon shape. If we look at the top view. And there is actually a structural transition here. So you see each droplet, after they deform so much, each droplet sits in the middle of 4 droplets from the other layer. So this differently, I hope you can all identify the 2 different layers because the focus is a little bit different. Like this droplet sits in between this little bit lighter gray boundary is from the other layer, sits in between this drop, this drop, this drop, and this drop. Okay. Then actually this inset shows the 3D structure of these double layered droplets. So actually they are on the side, on the plane wall, we have hexagon, but in between actually the structure is quite complex. We call this structure Ferrier Toth honeycomb or FT. I just call it FT honeycomb. This is from double layer packing of droplets. Then if we cross-link the droplets at this state, we will get exactly the same structured microgel particles or hydrogel particles. So in this case, we use polyethylene glycol diacrylate is one type of very common hydrogel, at 10%, meaning each of these particles have 90% water, which is supported by 10% interconnected polymer chains. So if you dry them in air, just leave them in the air and completely remove the water by evaporation, this dry particle will remain the shape of this wet particle. This is very interesting. And then this is an SEM picture, which has to be on the dry samples. They remain the shape. And if you add water onto this dry particle, they will swell and recover their original volume. So as I mentioned, there is a structural transition in this drainage process. So if we look at the pictures here, initially it's this, we call it beehive honeycomb structure. Then after you remove a lot of the continuous phase, they become FT honeycomb structure. These are 2 different structures. And we calculate and we assume, or reasonably assume that in this emulsion or even foam structures, the surface energy is the dominant energy in this system. Surface energy basically is the proportional to surface area. So it's the surface area multiply interfacial tension. So there are so much surface in this system. So surface energy is dominant, which is proportional to the surface area. So when we calculate the surface area between these two structures to see which one has a lower energy, which should be the preferred structure that we can get. Right, so we calculate the energy using a software called the Surface Evolver as a function of the droplet volume fraction. And we see that when the droplet volume fraction is increases above 0.935, about this value, this Toth structure has a lower energy, which is this structure, panel B, has a lower structure. This is consistent with our observations, right? When the droplet volume fraction is very high, meaning continuous phase is removed a lot, then this structure is preferred. Any questions?
I have one, Professor, about the other graph.
This one?
No. This
Which graph?
slide 10. The slide next one. The other graph, the first one. I don't get the axes. Like, what's the independent, dependent axis supposed to represent? I don't get that. The FT honeycomb percentage
You
and
mean
then the
between
beehive.
energy? You
sorry?
mean this graph? Energy,
No, the other
do you
graph.
mean this graph? Energy and
That one.
this
yes.
one?
Yes. Could you
Oh, okay.
explain that? I'm confused a
this
little bit
one is-
about the axes.
Oh, okay. So this is from experiments. So the vertical coordinate is the beehive honeycomb percentage. So basically, we have a sample. Then as we remove the continuous phase, as the droplet volume fraction increases, we see that in certain area, the beehive structure started to transform to Toth structure. Like we see a transition from this structure to this structure as the drainage takes place. Then within a larger scale sample, we will see this transition happened not suddenly over the whole device, but it may happen first in certain area and then gradually increase. So we count the number of droplets in beehive structure and in Toth structure. Then we plot the percentage of the beehive honeycomb structure droplets. For example, we may have 1,000 droplets and we see 100 beehive structure, then which means the beehive structure percentage is 0.1. So we count this percentage as a function of droplet volume fraction. And we see that when droplet volume fraction is below 0.952, we have more beehive structure. And when this droplet volume fraction increases even higher than 0.92, we have more Toth structure. Of course, we may have some defects. That's why there are some other structures in the sample, but that's the nature of experiments. That's common. So this transition volume fraction from experiment is about 0.915, but from completely pure theoretical prediction, theoretical modeling is about 0.93. So this is reasonable. This discrepancy is reasonable between simulation and experiments. Both shown that we have a critical volume fraction above which we will have Toth structure, because this structure has a lower energy than the other at high volume fraction, droplet volume fraction. So yeah, so there should be another video here showing how this structure transition takes place, but unfortunately, I don't know why this videos cannot play. Okay, so the reason for this structural transition from beehive structure to the other is actually because of this beehive structure is not stable at high droplet volume fraction. It's against some so-called Plato's law, which I may just skip. So basically, this law requires that a stable structure should have these two features. One, every 4 edges meet at one vertex with the angle of 109 degrees. And feature 2, every 3 fumes meet along an edge at an angle of 120 degrees. So if we take a close look at this beehive structure actually at very high concentration of droplets, we have some vertex at which 8 edges meet at that point, which is not stable. That is why we see that structural transition. This is just the mechanism that we figured out for this structure transition. Then, okay, so continue the story. If we further increase the distance between the 2 plates, we can have multiple layer droplets packed in between. Then at relatively low droplet volume fraction, it looks like this. Then when we increase the droplet volume fraction, again, it has a transition from this FCC to BCC. And these 2 cells shows the 3D structure of 2 droplets, 2 deformed droplets. So if we cross-link them, the droplets at this stage, then we can obtain the hydrogel particles with exactly the same structure. And we call this Kelvin structure. So this Kelvin structure is actually a 14-phase structure with with 6 hexagons and 8 squares. Again, this is another video, shows that we can get perfect Kelvin structure throughout, I think, 7 layers. Okay, so this Kelvin structure actually comes from, this is some very interesting background story about this structure. It comes from a conjecture proposed by Lord Kelvin in 1887. This Kelvin is the same Kelvin that proposed the unit for absolute temperature. We have the temperature unit Kelvin. This is the same Kelvin. So he is a genius person that has a lot of achievements in physics and mathematics. So he came up with this question. So how to partition a space into equal finite volumes with the minimum surface area. So maybe I will first give you a 2D version of his question. So how, if we have an infinite plane, just one 2D plane, how to partition a plane into equal areas with the minimum parameter. So if
The
we want
plane
to
is infinite, right?
partition a plane, yeah, infinite. We partition them into equal areas. Which structure should give us the minimum parameter that separate the areas? Can you guess? Think about this 2D question. Actually, you saw this structure in the previous slides. So the answer is this: hexagonal packing. You partition a plane into this hex, gives you the minimum parameter, minimum length. There are only a few options that you can separate a plane completely with the same area. For example, you can use square. You can also use triangles. You can use hexagon. And if you compare these 3, hexagon has the smallest parameter, right? And Kelvin's conjecture, Kelvin's question is a 3D version of this question. How to partition a space into equal finite volumes with a minimum surface area. And he is very clever, and he proposed a solution to his question, which is Kelvin structure. That's why we call it Kelvin structure. So if this picture shows a little bit larger scale. So how multiple Kelvin structure packed together, and they will occupy the space without any, void in between. So this structures, as I said, is 14 faces with 6 hexagon surface and 8 square surface. And actually, this Kelvin structure is slightly different from this polyhedral shapes, is because some of the curves, some of the edges are slightly curved, and also the surface, the hexagon surface is not flat. It's like saddle shaped, but this square surface are flat. But these hexagon surfaces are not flat. This is to be consistent with the Plato's law, if you recall. And I mentioned that every 3 surfaces meet at one edge at 120 degrees. Every 4 edges meet at a vertex at the angle of 109 degrees. So to comply with that Plato's law, some of the edges have to be curved a little bit. But anyway, Kelvin is so clever that he proposed this solution. And then after that, for over 100 years, no one can prove if this solution is correct or not. That's why it's called a conjecture. And no one can propose a better solution of this question. Until 1994, over 100 years after that, a group led by Ware and his student called Phelan, they use numerical simulation. They use computers to find a new structure that is 0.3% better than Kelvin's, meaning it still consists of equal finite volumes, but the surface area is 0.3% smaller than the Kelvin structure. People call it Ware-Phelan structure. This structure is very complicated. So it has a periodic units consisting of 8 elements. They all have the same structures. They all have the same volumes, but 6 of these 8 structures are exactly the same, have the same geometry, and the other 2 have a different structure, different geometry. So they all have the same volume, but 2 different structures. And this group with 8 cells form a periodic unit. They just, repeat Ware-Phelan structure. So actually, this Ware-Phelan structure is better than Kelvin. It's proved it's better than Kelvin. But interestingly, people just couldn't observe this structure in real experimental system. So we know that this minimum surface area problem can be experimentally studied using foams or emulsions, because we know that foam and emulsion system are dominated by surface energy, which is proportional to surface area. So those foams and emulsions should automatically have the structure with the minimum surface area, which is a perfect model experimental system to study this problem. However, in the real foams or emulsions, people just couldn't observe Ware-Phelan structure, although we have observed the Kelvin structures a lot. So why is the reason there? The first realization of a Ware-Phelan structure is actually the water cube, which is built for the Beijing Olympics, Beijing National Aquatic Center. So the architecture that for this building actually inspired from the Ware-Phelan structure and designed this building according to WP structure. But in reality, only until a few years ago, in 2012, people for the first time realized the Ware-Phelan structure in the real foam structure. And what they did is actually they used a 3D printed container with 5 surfaces, has the same structure as a real Ware-Phelan. They 3D printed this container. I have seen this box. I mean, the author of this paper just came to visit our group, and they showed me this box, which is a few centimeters large. And inside, they packed 1,500 bubbles into this box. So each bubble is 2 millimeters in diameter. So they're pretty big, actually. And by using this 3D printed box, they for the first time realized a Ware-Phelan structure in foam systems. Under microscope, they look like this. So then what I did is actually use a templated directed template using 2 parallel plates with some hexagonal pillars as the guide to guide the packing of droplets. The reason why people couldn't observe Ware-Phelan structure is actually because this structure is not compatible with the flat boundaries that we usually have for whatever our common containers. We have to have some container to hold the droplets, right, or bubbles. but this structure is not compatible with the flat surface. So we will have to use some template directed, some template with some structures to be compatible with the structure, to be compatible with wear-filling structure. And then also with this simple structure, which is made by soft lithography, PDMS plate, we also realize the wear-filling structure. Also, we polymerize them to get this, 12-phase and 14-phase microgel particles, which are the same structure as the two. You remember I mentioned two structures in wear-filling, which are these two. And we prove that they are really wear-filling structure. Okay, so this is the first example that how we use microfluidics and a little bit, physics, packing them and form non-spherical shaped hydrogel particles. This is the first example. The second example also comes from single emulsion droplets. So in this case, we generate some liquid crystal droplets. In particular, these are cholesteric liquid crystal droplets. So I'm not sure how much you know about cholesteric liquid crystal. I just want to share maybe just to share one. This is the website about cholesteric liquid crystal. So basically, liquid crystal is some matter that sits between solid and the liquid. So it's still, it can flow. Liquid crystal can flow. It's a liquid, but the molecules in the liquid crystal has some structure, well-defined structure. For example, for a cholesteric liquid crystal, so those liquid crystal molecules are all like they all in the different layers. So each of the droplet has a rod shape. Many of them have a rod shape, although it's a molecule. Okay, roughly the rod shape. So they sit into different. They form different layers down on that layer, and they all have the same direction, although they are random. But all the molecules, the rod-shaped molecules, have the same direction on one layer. Then the next layer, they tilt it a little bit. They have a slight, the angle of those, the direction of those molecules have a small angle from the first layer. Then the next layer, the angle changes again a little bit. Then the layer, it changes again. So then on the macroscopic scale, you have this helical structure. So each layer, the droplet, the first layer this direction, then the second layer twist a little bit, the next layer twist. Then you form this helical structure. So this is very unique helical structure, gives this cholesteric liquid crystal some very interesting optical properties. It's all because of the molecular structure on the micro scale. Okay, so now let's go back to the slide. So our collaborator in Kent State University, Liquid Crystal Institute in Kent State University, they simulate a special, they synthesize a special cholesteric liquid crystal drop. So excuse me, I will, my laptop ran low of battery. Okay, so this liquid crystal that they synthesized can reflect different colored light when you give the material some stimulus. For example, initially it may reflect only red light. And if you shine, now I forgot, if you shine UV light, or if you shine the visible light, then the reflected light color can change from red to orange to yellow to green, all the way to blue, to purple or blue, the all visible spectrum. Then it can recover, the reflected light color can recover from blue to red if you shine. So basically two trigger. One is UV light at the 300 plus nanometer. The other is visible light. So then by shining them with two different lights, you can trigger this cycle. You can change the reflected light color. Then we use microfluidics to make this very small, about 50 micron in diameter liquid crystal droplets. Then we can implement, we can control the color of each individual droplets onto each individual droplets. So we can realize some very interesting, like a flower structure, or some other structures that I didn't show here. And also we discovered a so-called photonic cross-communication process, meaning, so when you shine light onto these droplets, I don't know if I have I don't include the schematic here. Yeah, so it's hard to describe why you have these blue rays. We only have these blue rays in between two droplets. So like here, it's a single droplet, so we don't have any blue rays. And in this picture, we actually have two droplets here, contacting each other. And we have the two blue rays towards the other droplet. If we have three droplets, so this very bright dots represents the center of each droplet. When we have three droplets, we have this blue rays also in between any two. In this case, we have four different droplets. In this case, 5. In this case, we have a plane of hexagonal packing liquid crystal droplets.
Yes, sir.
So this is because of, yeah.
Sorry to bother you, but I was just wondering, does it matter how far the droplets are? How does that affect the, because
that's a great question. Yeah.
Yeah, because I was just wondering,
yes, it does.
The last picture, and it's like,
yeah. So actually, you see, it's more than 6 rays, right? The brightest 6 are from the 6 neighbors. But for example, between these droplets and this droplets, you will have a much weaker blue arrays as well. And actually, it depends. The intensity of this blue rays depends on the distance between the two droplets. That's a great question. I didn't put a separate figure for that phenomenon that we
did you measure to see how,
I didn't include that.
Did you measure to see how far along the droplets are where there's no connection?
A few diameters of the droplets, a few times diameters.
I see. Okay. Thank you.
Let me see if I can show you. So actually, let me start a new share. This is from the paper. You can see this communication becomes weaker as the distance between the droplets increases. This is a very strong communication. When it's far apart, it's weak. And when it's very far, we cannot notice any communication. We cannot see the blue rays anymore. Okay, so let's go back to the slide. Yeah. Then we also, if we pack them into 2 layers, then we can, shining UV light from one side, then we can change the color of the top layer faster than the bottom layer. This is because, again, the color change is because of how much energy from the light absorbed by the droplets. So the top layer droplet absorbs more energy than the second layer. That's why you can change the color faster. So basically these materials, if we have a way to pack them in a larger scale and also secure them within some protection film, I would propose, then we can in principle have a liquid crystal based display that you can control it remotely. You don't have any electric component to change the color, to change the image. So it has potential applications as a display or even some biosensors that we can trigger them remotely by light. And the resolution of this display totally depends on the size of the droplet, which can be easily down to 50 micron or even smaller, on the order of 10 micron, that order of magnitude. This is already better than any of existing LED displays in the market right now.
Yes, sir.
But those are some potential applications. Yeah.
So does the spacing of the droplets aid in the resolution, or like how does it affect how the light changes?
How the spacing between the droplet change what? Affect what?
Affect the color changes.
Not really. It's all, the color change depends on the energy it absorbs from the light, how much light energy you absorb. So it depends on the distance between the light source and the droplet. It doesn't, so the color of the droplet is represented by the middle, the very bright point in the middle. Although we can make them larger, it's just from our experimental setup, you can see the color from the middle point very clearly. The distance between the droplets doesn't really affect. The distance between the droplets influence the blue rays, the intensity, not the color in the middle point.
So the amount of light it absorbs depends on the intensity.
Right.
Okay.
Energy basically is intensity multiplied the exposure time.
Okay.
Yeah, the color depends on energy you absorbed. So it changed from like blue all the way to red, and then if you shine another type of light, change a different wavelength, then the color can change back from red to blue. So this process can repeat forever, many times. Okay, so these are two examples of multi-scale, micrometer scaled functional materials from single emulsion droplets. Then I probably have only time for introducing another example on double emulsion. Let's look at this example. This is microfluidic fabrication of monodisperse elastic capsules. But first of all, we fabricate monodisperse double emulsions, and then we transform them to solid shell capsules. So, okay, so this is a schematic showing how the double emulsion droplets are generated. It's slightly different from regular glass capillary devices. We basically have three phases, water, and then an oil phase, and then another water-based solution at the outer phase, inner, middle, outer phase. So in the middle layer, it's actually a polymer solution, a polymer dissolved in an organic solvent, which is not miscible with water. The outer phase is water with TVA acting as surfactant. So then when these three different phases meet at the junction, you can generate double emulsion droplets. And by using this device, we can have the emulsion droplets have a very, very thin oil layer, the yellow layer, very thin. How thin? Less than 1 micron. In the liquid form, the thickness of the yellow oil can be less than 1 micron thickness. Then after we have these droplets, again, this cannot play. After we collect these double emulsion droplets in a container, so the organic solvent that we used for the middle phase has some solubility in water, not completely miscible, some solubility. But this solubility enables this organic solvent to diffuse into water. We use, if I remember correctly, I believe we use THF, which is very strong organic solvent. It has the solubility around 20 to 30 grams per liter, some solubility. So it diffuses to water. Then the polymer originally dissolved in that solvent will precipitate, will be left to form a solid shell enclosing the original interface water droplet. So eventually we will have a solid shell capsule with very, very small thickness. And after it becomes solid, then we take, again, use SEM to look at the thickness of the shell, which is 150 nanometer thick. Remember, in the liquid phase, it's about 1 micron, so a few times of this. After we remove all the solvent, the solid thickness is 1 order of magnitude smaller. So we can control this thickness by controlling the flow rate of different phases and also controlling the polymer concentration in the original middle phase. And also, in this case, we use a very deformable, we use a deformable polymer. So it's like elastic polymer. So then the resultant capsules is very deformable as well. So for example, we add some fluorescent dye in the middle to show where the capsule is, and we inject them through a constricted channel like this. And you can see that even it deforms so much, the throat size is less than half of the original capsule size. But the capsule shell is so deformable that they can hold the inner core very well without releasing its cargo. So we use it to transport surfactant into two-phase in porous media. So I actually showed you this these two images, which we obtained from micro-CT. If you remember, we are mimicking the surfactant flooding process. We encapsulate surfactant at relatively high concentration within those capsules and release them only at the interface, because these capsules, the shell, can be dissolved by certain chemicals in the oil phase, and therefore they only release their cargo at the interface. Yeah, I think I showed you these results. So then we use it to deliver surfactant and to reduce the residual oil in a model porous media system. We compare the use between this capsule flooding and the regular surfactant flooding, meaning we use the same amount of surfactant. In one case, we encapsulate them in the capsules and deliver them to the interface only at a high concentration. The other case, we dissolve the surfactant, the same amount of surfactant, directly in water. So we flood surfactant solution into the model porous media at a relatively low concentration. And we see that For the regular surfactant flooding without using capsules, we see a 12% reduction of the residual oil. But if we use capsules, we see a 30% reduction of the residual oil. Although we cannot interpret these two numbers quantitatively, it doesn't mean that capsules can improve, more than twice of the reduced residual oil. But this we can see it's clear that by using capsules and deliver surfactant at high concentration to the interface, we can have better oil recovery efficacy. This is a real example. Also, this is another example from double emulsion droplets. We can form the so-called giant unilamellar lipid vesicles. Basically, this vesicles has a membrane with the same component as the cell membrane. We know that our cell membrane are actually a lipid bilayer. So 2 layers of lipid molecules. Lipid molecules are like amphiphilic. So each molecule has 2 parts. One part is hydrophilic, one part is hydrophobic. And when they form this lipid bilayer, actually the hydrophobic part from 2 molecules facing each other, but the hydrophilic part of the molecule will be exposed to both inside and outside. Maybe I can find another. Lipid bilayer. Yeah, so if you see this website, lipid bilayer, each molecule has a hydrophobic tail and a hydrophilic head, and they form a bilayer with the hydrophobic tail facing each other in middle, and hydrophilic head toward outside and inside, because both inside and outside are water-based. Just like our cell, inside is liquid-based, outside also liquid-based. So we can, from microfluidics, we can form some giant lipid vesicles, very big, much larger than cell. That's why we call it giant. This is about, I think, like 100 micron in diameter, slightly less than 100 micron. So you can form this lipid vesicles, and if you have 2 different lipids, and usually the same kind of lipids tend to stay together, and the other, so if you have 2 different lipids stand with blue dye and red dye respectively, and over some time you will see this phase separation. We call them phase separation. The same lipid will stay together, and eventually it completely separates into 2 parts. And this system can be used to study the interaction between different lipid molecules, which are not doable with any other systems. This is just one very brief example. Also, another example that I didn't mention is this. Okay, maybe I will just skip this. Okay, and then here, the last example is a complex microcapsules from triple emulsions. So this material was developed to encapsulate very small molecules, such as perfume. Like, we know that its molecules or drugs are large molecules, so it's relatively easy to encapsulate them in the core. However, if we really want to encapsulate some very small molecules like perfume, some very small organic solvents, then by using 1 layer of shell is not enough to encapsulate them inside. So we'll have to use 2 layers, 2-layered shell for a better, cargo retention. So in this case, we have the perfume molecules encapsulated in the liquid core, in the water-based core, one. And then we have a hydrogel, very thin layered hydrogel shell surrounding it first with the number 2 on this schematic. And then another polymer, thicker polymer shell outside the hydrogel shell, number 3. So we have a double layer shell encapsulating this water-based core, then surrounded in another outer water phase. So we have this structure, and we have, so we have played with the thickness of different shells and characterize the retention efficacy of these 2-layer capsules. And we have seen that, and also the thickness depends on the flow rate when we generate them under microfluidics. So we prove eventually that by using this double-layered shell structure, we can have small molecules well contained, maintained in the core for over a month. So this is actually a project supported by, I believe this is supported by P&G. So they wanted to, have some product that, for example, you can encapsulate the perfume within some little droplets or little capsules, and suspended in your cream. And only when you scrub the cream onto your skin, mechanically you break these capsules, then the perfume will be released. So only when you apply the cream, then you release the perfume. So we were participated in early, research stage. I'm not sure what's going on right now for that project, if there's any real product available on the market with this concept. I'm not sure. Yeah. So this is some real applications of this kind of microcapsules in our daily life. Doesn't have to be for drug delivery to cure cancer or whatever, but we can really use it in our daily, personal product. Yeah, so I just use like an hour or so to give you a few examples that I have participated, like the projects that I have participated in developing different kinds of micro materials using microfluidics as a technical tool. So yeah, so now my group is more focused on using this microfluidics generated products as a model system to study fundamental physics or engineering problem. But still, whenever we have a chance, we're still interested in developing this functional materials. When you have a good idea, you can quickly try it out with microfluidics. It's a very good proof of concept system. Eventually, we probably want to scale up the production using non-microfluidic way, or if we can have ways to scale up the microfluidic device fabrication, that will also help with this industry, for this industry. So yeah, so I hope this topics are interesting to you. So after the midterm, we'll have more chance to discuss the details of, we have a variety of materials that can be produced with microfluidics. Do you have any questions about these?
I have one, Professor. I know that you said the second structure, not the Kelvin one, the other one, the pledge, WP, pledge, the structure, the second one, the complicated one. You said that they 3D printed it so that you can visualize how it looks like in 3D form. Have you known? I know you said that's only 2 millimeters, so it's kind of quite large for the for microfluidics. Do you know if they attempted it since then? I mean, it's been a few years, and there has been newer 3D
Yeah,
printers.
so I see. I don't think that they because probably also because of the resolution of 3D printed part cannot be very small, very high. That's why they have to use a larger bubbles. I don't think they have done something further on 3D printed templates. But what we did is to use the soft lithography to make this template. In this case, the droplet size is 150 micron. So we
I
use
see.
microfluidics generated droplets. Yeah.
I know it's 0.3% better than Kelvin's, but do you think that 0.3% is optimal? That should it be better? Like it's not worth that 0.3% increase and just stick with Kelvin since it's easier and to produce, or is that 0.3% actually worth going through that whole process of to manufacture it? I guess.
I see. Oh, yeah, that's a great point. So no. So to realize where fill-in structure is not because we want to use them really for some other real application. It's just this is probably mainly studied by some mathematicians and physicists. It's just to fill our curiosity. This actually. Now people have proved that the Kelvin's problem, the Kelvin's conjecture, cannot be solved analytically. Meaning this problem, you couldn't prove a solution is correct or not. It's just couldn't. Analytically, you cannot solve it. So then we will have to use other ways. For example, from experiments or simulation, but from experiment or simulation, we can only, if we find a new structure, like how where fill-in is discovered, how where fill-in structure is discovered, we can only propose new structure that prove it better than the existing structure. You still cannot just prove this is the best structure. No, we couldn't.
So how did they figure out 0.3% better or optimal than Kelvin's for structural purposes? I know you said they use a computer.
Oh, you can calculate. Yeah. They use the soft surface evolver. There is a software for that purpose. So if you give it a structure, for example, how the software works is that you input the structure with a flat surface, and then the software will help you evolve. Because the real structure is not a flat, some saddled shape and some curved edges. So the software will help you evolve until optimize the structure with the curvatures. But first of all, you will have to come up with a structure that may be, better than Kelvin or where fill-in. Then you tell the surface evolver software, then it will eventually calculate the exact surface energy or surface area for you.
Got it. Yeah. Okay. Thank you.
So you can calculate the surface area, no problem, but you couldn't ask them to find the definitely minimum one. No. There's not much real applications for where fill-in. As you said, it's only 0.3% difference. Okay, thank you for your questions. Those are excellent questions. Yeah. So if you don't have any other question, then we will stop here. The next Wednesday, we will have our midterm. Okay. If you want, you can check Blackboard on the midnight of Wednesday. You can start early. Okay. Yeah, so we don't meet next week. Right? So you can work on your own midterm.
Wait, will this
okay, thank you everyone. Then I will see you. Pardon?
Sorry, will this be on the test too?
No. What we discussed today will not be a midterm. No.
Okay.
Also, yeah, I will include it in the instruction of midterm. But if you work with someone for your midterm, for whatever questions, you will have to indicate it, who you are working with about which question. I will include it in the instruction, just to. It's open to everything. If you want, you can work with your classmates, but you will have to, you know, give credits or indicate in your exam. Okay, then I will stop the meeting here. See you next time.